A 71 kilogram rocket, that's its total mass, burns 51 kilograms of fuel at a rate of 2.1 kilograms per second with an exhaust velocity of 650 meters per second. What are its initial and final acceleration as it takes off from Earth? And then notice I'm telling you the thrust here. That's because everybody messes that up. On the test, you're not going to have that, so you just got to be careful, okay? Okay, so the first thing I want to do is I want to figure out the initial mass, right? And that is the initial mass right there. That's the fuel and the rocket. Sitting on the launch pad has a mass of 71.0 kilograms, okay? The final mass is going to be the 71 kilograms minus the 51 that is the fuel, okay? So 71 minus 51 is 20 kilograms. So in the last molecules of exhaust gas are leaving the rocket, it's got a mass of 20 kilograms. And we'll use that for the final acceleration, okay? Now the next thing we want to do is we want to figure out the thrust of the rocket, okay? So we're going to go force times time is mass times change in velocity, okay? Now, there's easy ways to do this and hard ways to do this, right? If we use that as the mass, then we got to figure out how long it takes to burn. But I know that this is 2.1 kilograms in 1 second. So that's what I'm going to do. I'm going to go 1 second is 2.1 kilograms, okay? Our exhaust velocity is 650, so we're going to throw that in for our delta V. Really what we're doing is figuring out the force on the fuel, which is, of course, the force on the rocket is the opposite of that, right? We push the fuel down, the fuel pushes the rocket up, okay? So literally, we're just going to go this times this, okay? So 2.1 times 650 is equal to 1365. So the thrust of the rocket is 1365 newtons. So just make sure whenever you do this, that whatever you put here is the fuel that is burned in whatever this amount of time is, okay? Since it was 2.1 kilograms per second, I said 2.1 kilograms in 1 second, okay? All right, now all we really have to do is we've got to figure out the initial and final accelerations, right? So initially, we've got a rocket that has a mass of 71 kilograms. And there is a force of 1365 up. And the force down is going to be, let's see, 71 times 9.8. So that downward force is 695.8. So 695.8. All right, now we're set. We've got 1365 up and 695.8 down. And then that equals the mass, 71 kilograms, times A. All right. So 1365 minus that 695.8. That's 669.2, and I'm going to divide by 71. All right, and I get 9.43 roughly. It's 9.425. I'll say 9.43 meters per second squared. That's a 4. All right, so that's our initial acceleration, okay? The final acceleration of this thing is going to be, let's see. Now it's got a mass of 20 kilograms, right? Okay, the force of gravity is 20 times 9.8. Is that in 1,196? Let's do it. 20 times 9.8. 196. The force upward is still going to be 1,365 newtons. And now we set this guy up, 1365. That equals 20 times A. Okay, so 1365 minus 196 is 1169, and then divided by 20. That's 58.45. Okay. Ta-da. So a lot more acceleration, right? Because there's less force of gravity opposing it, and there's less inertia, right?